I would like to be the first to welcome you to tonight's lecture. My name is Nicholas DiMancio. I'm a professor and head of the Department of Architecture here at MIT. And it is a great pleasure for me to welcome you all to the 10th Annual Edward and Mary Allen Lecture in Structural Design. Before we go much further, I'd like to begin with our land acknowledgement. MIT acknowledges Indigenous people as traditional stewards of the land and the enduring relationship that exists between them and their traditional territories. The land on which this lecture takes place is the traditional unceded territory of the Wampanoag Nation. We acknowledge the painful history of genocide and forced occupation of their territory, and we honor and respect the many diverse Indigenous people connected to this land on which we gather from time immemorial. Now, there's always a danger that words like these can be a substitute for action, but this department in particular is dedicated to the synthesis of words and actions, of thinking and making, with the goal of crafting a more just, beautiful, and sustainable world. Few events in our lecture schedule better represent this goal than the Allen Lecture that you're watching tonight, and few individuals represent such a synthesis better than Ed Allen himself. The Allen Lecture brings a distinguished structural designer to MIT each year to share their work in a public lecture and to work with students in a design setting. The inaugural Allen Lecture was delivered in 2012 by the celebrated engineer Jörg Schleich from Germany. Over the past decade, we have been truly fortunate to host some of the most inspiring and creative designers from around the world here at MIT, including Bill Baker, Les Robertson, and Sortine C., Janet Echelman, and more. We are very pleased to have Mary Allen and members of the extended Allen family with us tonight in our online audience, and to have the opportunity to thank her and her late husband, Edward Allen, for their foresight in endowing this important lecture. Ed Allen was a member of the faculties of Yale University and MIT, and frequently taught as a guest at other institutions around the world over the past 30 years. He was the best-selling author of numerous important books, including Fundamentals of Building Construction, The Architect's Studio Companion, Form of Forces, Shaping Structures, and a personal favorite of mine, I brought my copy from my office, The Responsive House, with its amazing design by Muriel Cooper. For his inspired writings and teachings, Ed was the recipient of the 2005 Topaz Medallion for Excellence in Architectural Education, awarded by the American Institute of Architects and the Association of Collegiate Schools of Architecture for lifetime contributions to architectural education. Particularly given the scale of all these contributions, we were truly saddened when Edward Allen passed away in July of 2020. His love of learning and enthusiasm for building and design will continue with a generous gift to MIT to support activities and teaching that will improve the ability of architects and engineers to design efficient, economical, and expressive structures. All three of those words are essential to Ed's approach to design and construction. And this legacy includes now the Edward and Mary Allen Lecture in Structural Design. Professor Mary Allen is also a distinguished educator and scholar, having taught biology at Wellesley College for more than 30 years, where she is particularly noted for mentoring undergraduates in research. She was awarded the Wellesley College Pinansky Prize for Excellence in Teaching in 1986, and the American Society of Microbiology Karski Foundation Distinguished Teaching Award in 1995. Please join me in thanking Edward and Mary Allen for making tonight's lecture and all its effects on our school possible. And now, let me please invite Caitlin Mueller to introduce tonight's speaker.
Hello, good evening. It's my pleasure to introduce tonight's speaker, Professor Sigrid Adriaenssens. Sigrid's research interests lie in the mechanics of large-span shells and membranes under construction and extreme loading. She has been working on a comprehensive framework to open up new avenues for accelerated discoveries and automated optimal structural designs. In addition to applications, she's used this framework to successfully innovate structural and architectural systems ranging from macro-scale adaptive shading shell devices to large-scale storm surge membrane barriers. In all of her work, she uses her practical experience gained while working as a structural designer with Ney & Partners 2003 to 2006 and Jane Wernick Associates 2002 to 2003. In 2021, this year, it was a huge year for Sigrid. I'm going to list a number of awards that she's won. She was named a Fellow of the Structural Engineering Institute by the American Society of Civil Engineers, elected Vice President of the International Association for Shell and Spatial Structures, awarded the Matthias Rittmann Digital Futures Award from Tongji University, and the Pioneers Award from the Spatial Structures Research Center at the University of Surrey. Congratulations, Sigrid. She chairs the ASCE Aesthetics and Design Committee, as well as the ISS Concrete Shell Roofs Working Group. She is the co-editor of the International Journal of Space Structures, and she directs the Form Finding Lab at Princeton University, where she teaches courses on nonlinear mechanics of solids and slender structures, structural design, and the intersection of engineering and the arts. At Princeton, she's Associate Professor of Civil and Environmental Engineering and Director of the program in Mechanics, Materials, and Structures. Sigrid earned her bachelor's, master's, and PhD at the School of Architecture and Structural Engineering at the University of Bath in the UK, a very special place. In addition to all of these achievements from her official biography, I'll share that Sigrid was also the co-organizer of the 2018 Symposium of the International Association of Shell and Spatial Structures here at MIT, together with John Oxendorf, Bill Baker, and me. And we called it the Creativity in Structural Design. And this wonderful event brought 650 people to our campus to celebrate design and mechanics. It was a highlight for us and greatly enhanced by Sigrid's energy, insights, and leadership. We are so thrilled to welcome her back to MIT today to deliver tonight's Edward and Mary Allen Lecture in Structural Design. She's entitled this Harnessing Extraordinary Mechanics for Structural Design. And given the challenges that we must urgently confront in the immediate future, I am convinced that harnessing the best that physics can offer for the benefits of design is a critical path forward, and I hope Sigrid's lecture will convince you of that as well. Following the lecture, there will be a question and answer period that will be facilitated by collecting index cards that you were handed when you walked in. Please jot down your questions throughout the lecture, and our staff will collect the cards from you, and they will be read aloud by me, the moderator. We will not be passing microphones around the room. We'll also be collecting questions from our webinar, so if you have questions and you're watching online, feel free to add those as well, and we'll do our best to get to them in our live talk today. So with that, with no further ado, please join me in welcoming tonight's speaker, Professor Sigrid Adriaenssens.
Thank you very much, Caitlin. I'm very happy to be at MIT today. Unfortunately, I did not know Ed Allen personally, but I use his books all the time with my students, so I'm very grateful that I'm here to deliver this annual lecture. About 11 years, I moved to Princeton, to the United States with my family. I was at the time actually living in Belgium, and I had replied to an ad for a position at Princeton University. And I had gone to a talk where they said, creative people should always tackle bigger and bigger challenges. And I thought, wow, I'll just apply to Princeton. That seems like quite a big challenge. I'll never really get that. And so many years later, I'm here. But so we moved to New Jersey, and one of the things that we discovered, which is a pleasure of New Jersey, is the shore. And so in the beginning, we were going to the shore quite a lot, but when we were driving on the motorway, like this one here, this is Route 1, I was always struck by these bridges that we were going underneath, because they seemed to me so massively constructed, the idea that you have to use a lot of material to make these crosses. And this also surprised me, because the construction industry is one of the most resource-intensive industries. And I was surprised why, for example, that shape of that bridge, if we thought about it as an integral bridge, could not look like this. This would, could take all the forces in a very efficient way, maybe look more elegant, and definitely save more materials and maybe be more cost-effective. Now, when we get to the Jersey Shore, and actually sometimes we also go to the beaches in New York, this is what you see, a lot of people. And we know that we're going to be more and more people, especially by 2050, it's projected there will be an additional 2.1 billion people on the planet. And all these people are going to need houses, they're going to need offices, and it's projected that in North America alone, we're going to need 65% more floor space, which is huge. This is in contrast with the productivity of the construction industry. So you see here on the left a graph showing the total economy and the construction industry and labor productivity. And things are not boding very well for the construction industry. Also, if you look at construction practices, they don't really differ that much from the ones we had about 50 years ago. More challenges. One is the depletion of natural resources. As you know, we need materials to build stuff. For example, in concrete, we need sand. And so we use about 40% of those resources. At the moment, we pour about 10 billion tons of concrete a year. By 2050, this will be 60 billion concrete per year. We are already experiencing shortages in sand. And it is predicted that over the next couple of years, sand will not be an affordable commodity anymore. Also, as you know, when we build stuff, we build them in a very wasteful way. And so about 29% of the landfill in the US is filled with stuff coming from construction sites. And then I haven't even mentioned climate change. The construction industry contributes to a lot of the CO2 emissions. In 2017, they had to put a 4-month ban in Shanghai on construction projects going on because there was just too much, that was just causing too much pollution. And not only are we adding to the problem, we're also seeing the effects of climate change. And this is what happened in Sandy, during Sandy at the New Jersey shore, right? So we are seeing, because of climate change, we're seeing more intense storms and more frequently. And this causes enormous economic but also social losses. And what kind of surprised me after Sandy is that, at least in New Jersey, we kind of went back to business as usual. So basically, we rebuilt the boardwalks just like they were before, not really opening our eyes to what is going to happen in 10 years, 20 years, 50 years, et cetera, et cetera. So one way was to just go back to what we were doing. Another way was this example of this seawall, which was built in brick. So the idea here is, okay, we're just going to use a lot of mass. We're going to build a big wall and keep the nasty sea and the storm surges out. As you, of course, I don't really have to explain this, but now people cannot really get to the beach. Animals cannot migrate anymore. Also, property values going down. So I don't really think that this is the way that we should be going forward. I think it's very clear that we need to change what we design for, how we design it, and how we build it. And this is how I address these things in my research. What we design for, so I focus on slender surfaces, so that are membranes, shells, grid shells, nets, and extreme loading. This is loading due to the causes of climate change or maybe also natural hazards. In my work, I leverage geometry and mechanics. This is quite difficult because these things are related to each other, especially if we're talking about complex geometry and complex loading. We get loads that vary, that depend on the geometry, et cetera, et cetera. And then also we're going to have to think about how we build things. The National Academy of Engineering actually explicitly stated this in one of their 14 grand challenges, that we're going to have to really rethink our construction practices. And in that text, they kind of suggest that maybe we should be looking at computer science and robotics for practices that might be less wasteful. So in my research, I use form a lot, and of course, this is not a new idea. I'm not the first one to do this. Actually, if you look throughout history, people have been using form forever to span large distances. And you see here a graph. On the x-axis, you have time. On the y-axis, you have weight, and see that weight's actually a logarithmic scale, right? It's not just like a normal scale. And so if we start all the way with the pyramids, which are, of course, solid blocks, a lot of weight, making our way down through the Hagia Sophia, the mosques, the cupoles, the Gothic vaults, coming all the way down into the 20th and 21st century. And what you see there on the right-hand side is actually a close-up of the structures that are totally on the right-hand side of the graph. We have come to the point where we are designing, you will see some of the structures I'm showing you are extremely lightweight. Actually, they're so lightweight that if they were not designed in the right way and the wind comes, and sometimes the wind presses down on structures, but sometimes it also sucks it up, that they're actually so lightweight that the wind could actually lift them up, right? So we have to design them properly. Then there are some more challenges, and I put this in here because, especially when I'm talking with engineers, like in mechanical engineering or electrical engineering, I have to say that civil engineers and architects deal with other challenges. One is one of spatial scale, right? So things that are possible at the 10 centimeter scale are sometimes not really possible at a 10 or 100 meter scale. And what you see here is, and that is for strength, Galilei, you see a bone, the top picture is a bone, and below that you see a bone that is 3 times bigger. And you see that this doesn't really scale because area and volume don't really scale to the same power laws. So spatial scale is an issue. The other thing is time, right? We don't design mobile phones that maybe only last, I don't know, anything between 10 years to a year. We design and construct things that last hopefully 50 years, maybe 100 years, some 200 years or 1,000 years. And in that time span, these things that we design and build have to, first of all, not the materials have to stay, so they have to be durable. And also the things that we design have to resist all the loadings that it will encounter during that period. So this is one of my favorite domes. I'm going to talk about this dome again. This is the Brunelleschi's dome in Firenze, and it has obviously withstood a long time, but also it is in a seismic region, right? So it withstands earthquake loads. And then the last thing is that, compared to other disciplines or maybe even nature, we are limited by the materials that we can use. We are in quite a conservative industry, and that is, of course, because these materials have to last for a very long time. And so the materials are also going to potentially put a limit as in what we can be doing. And what you see here is actually a scale as well as the types of shells that you can experience at that scale. So how do I imagine a world then to look like? Well, I imagine a world where we are doing more with slender structural surfaces. So these are nets, they are membranes, they are very lightweight, therefore they have a very low carbon footprint, and they are redundant. That means that structurally redundant. That means that if they break somewhere, they're actually able to share their loads through their surface. So there are many load paths in these surfaces. So they're very resilient. Also, I look at geometries that can do very interesting things. These kind of structures, because of their shape or because of their topology, that means the way that their elements are connected, they can achieve properties that are not really possible with conventional structures. So I'm going to talk to you today about structures that can change their shape quite quickly and go back, that can amplify motion, that can adjust their stiffness, that can have extreme loading capacity, and also that can actually self-lock and almost construct themselves through gravity. So I'm going to talk about this in the context, of course, of an urban environment. So I'm going to talk, for this, for example, I'm going to talk about how can we design and construct large span thin shells that can withstand seismic loading. This would, for example, be in San Francisco. Or how can we design flexible barriers that can keep us safe? And actually, these are shark net barriers that are installed, well, under the water, as you can see. Or how can we use deployable storm surge barriers? This is in contrast to the brick wall, or not the brick wall, the stone wall that I showed you, which was placed in brick. How can we maybe make deployable barriers that can be deployed once a storm warning is out? And maybe these barriers can be replaced every 25 years so that they can actually be adapted for what the predictions are regarding climate change. Or how can we design buildings that actually adjust themselves to outdoor lighting and heating levels and make the life of their users comfortable while also reducing energy consumption. So those are the projects I'm going to talk about. I'm going to start about how we can use flexible shells for adaptive facades. So what are adaptive facades? Adaptive facades, and this is a rendering, this is not a real project. Adaptive facades are facades that can change their aperture to either let in more light or less light and also control the solar radiation. Traditionally, these things consist of rigid parts. So, for example, there's a very famous one in the Institut du Monde Arabe in Paris, which actually are like these kind of shutters that open and close. But so those are all rigid parts with mechanical hinges. And if you've been to the Institut du Monde Arabe, actually a lot of them are stuck because it's very expensive to oil all the bearings, etc., etc. So our thinking was, can we design flexible shells that open and close that don't need all this mechanical complexity? And it has been shown that using these kind of adaptive facades, we can save up to 40% of energy in buildings. So, so we were looking at inspiration for systems that use very little energy to make movements. And we started looking at plants. You might think that plants don't really move, but actually, because cactus doesn't really move that much, but plants do move to feed themselves, for example, the Venus flytrap, a very famous example, or to protect fragile organs like the mimosa plants, or to disperse seeds. And so we worked together with a botanist, Sasha Eisenman from Temple University, to identify 5 shape morphing strategies in plants. You have them here, all 5. So the first one is differential expansion, where you have a set of cells that swells and the other ones don't swell, and then you get kind of bending. The other one is torsional buckling of very slender elements, that is in the bird of paradise flower. Another one is where you have fibers that are laminated in different ways, and then, for example, you see this in pine cones that open and close. When they get wet, they open and then they close. That's because they have different fibers in different orientations, and when there is a change in moisture, some of them will swell and it will actually cause either twisting or bending. Then the Venus flytrap, we're familiar with that one. And then the last one is release of elastic energy. So we get a storage of elastic energy, and then there's a very sudden fracture and a kind of quite explosive movement. So we were interested in what I call shell geometry in mechanics. Shells, when they deform, they will prefer to bend rather than to stretch, because stretching is very energy intensive. It requires a lot of energy from the plant, and in nature, everything wants to do, everything in nature wants to do everything at a very low energy level. So if this thing is going to move, it's going to do this through bending. And in plants, like in the Venus flytrap, these movements are quite fast, they're quite accurate, and they're reversible. That means that it can open and close and open and close. So that were the plants that we were most interested in exploring. And the plant that we were most interested in, because we were trying to find a flexible shell, so we don't need any hinges, and for a adaptive facade module, for a shading device. And so the plant that we found that was most suitable was the Pseudohymium graminifolium. That's an Australian flower. And you see there on the left-hand side, it has a passive part, that's the blue part, and then it has an active bend. And that active bend allows both for twisting and bending, and that's exactly what we wanted for a shading module, because we want to kind of track or block out the sun as it makes a spherical path across the sky. We kind of want to block out that motion, and for that we need a shell that can do both twisting and bending. It turns out that geometry is actually the inside of a torus, so it can be described by 2 radii. And so we imagined also how in our shading device, our adaptive shading device, we would have an active component, which is shown there in the blue, and then a passive component that would not really change shape. And we imagined, indeed, with this inside of this torus, we can have this active part that moves. And we imagined how maybe we could actuate it by either contracting two diagonal wires, that would actually cause a bending motion, or if we contracted only one wire, that would cause a twisting motion. And we also studied this not just looking at plants, but we realized what we were looking for in shells are what we call isometries. So these are, an isometry is a length preservation. So that means that, when your thing changes shape, the line that originally was a straight line or was a line has not changed its length. So that means that you're actually working with something that's mostly working in bending, not in stretching, because stretching requires a lot of energy, and we want to use the least amount of energy to actuate these shells. We also found that Lord Rayleigh in 1888 had actually described a method for finding ways or geometries that will move a lot. So he said, well, if you look at a geometry, and we have there, for example, the rectangular strip, the inside of a quarter torus or a cylindrical strip, if you do eigenanalysis, then you will see how these shapes like to move easily, right? And so we found that indeed for the torus, the geometry that we had discovered in this plant, that indeed with that geometry we can, with very, very little energy, either twist it or bend it. And so we did many parametric studies of, what are the correct radii that we need, that use the least amount of energy. And so what you see there on the right-hand side is a plot of, on the one hand, the integral of the Gaussian curvature, and on the y-axis you see the isometry, and this is for symmetric loading. And you see that basically for almost all the parametric studies that we did, that this lies on a straight line. And so that means that, for all these geometries, when we deform them, they mostly bend, they hardly ever stretch, right? And this is what we want, because stretching takes up a lot of energy, which, would then translate into energy required to drive your actuation, which we didn't really want. So then, let's see whether this works. What you see here is a finite element analysis, where you indeed see that all the action is happening in the active part. When it's closed, so the way that we imagine this, when it's closed, so the actuators are smart memory alloys. When they're at rest, the shell is down. When you shorten both of them, they will move up and bend. And if you shorten only one, then it will twist. And with these two motions, the bending and the twisting, you can basically define shades that can block out the sun, if that is required, for any position on Earth. And so this is a rendering of the twisted motion fully open. It's also, I don't know if you've worked on facades before, but it's also important that you use not only block the sun and get appropriate daylighting levels, but also that they have a good view out. This is also very important. So here's when it's fully open, pretty good view out, when it's half open, and when it's fully closed. So that was a continuous surface. We're currently doing some other work, not on continuous surfaces that are changing shape, but on networks. And actually, the inspiration here comes from lace. So we worked with a lace maker to study bobbin lace networks. And what we found is when you make lace, not with circular rods, but with strips, so that means with elements that have like a rectangular cross-section, these things will pop out of plane. You might think of lace as a kind of flat thing like a dolly or something, but if you make it at a larger scale and you make it with strips rather than circular sections, these things pop out of plane. And so in one of the lace patterns, the torsion ground lace, we identified one basic unit that is responsible for that, and we call that a bigen. So basically a bigen consists of two strips that are connected together. And basically, you can fix the angle gamma between those two strips. And depending on that angle gamma, those strips are either going to stay in plane, or if you increase that angle, the bigen cannot really stay in equilibrium in that shape. It either pops out upwards or it pops out downwards. And so it's totally a function of the thickness, the width, and the intersection angle. And so we imagine what would happen if you propagate these bigens together, either with a small intersection angle gamma or with a large intersection angle gamma, and you basically end up with an undercurved or an overcurved structure. And now you can actually start making many stable shapes. So you can either pop them all out, or you can pop one in, one out, one in, one out, or you can do many different shapes. And so we did a study of if you have 6 bigens, how many different stable shapes can you make? And it says here not all configurations are shown. So there are many more. But we discovered that there's basically 3 different families. One is a family, and that is what you see there at the top, where they are either, where the units are either going in, let me get this started, where the units are either bent or buckled inward or outward. Then there is another family of shapes where the ring kind of loops back onto itself. And then there is a third family of shapes where, that are in equilibrium, that is the shapes that are twisted. So I think this is very interesting because this has applications for example, structures or materials that have to be packed in very tight spaces and then expanded, so for example, in a space exploration. So this is for a ring, but you could also imagine this, for example, in a network, right? So we now have a number of bigens that are put in a network, and what you see here, we have the red and the green units that either pop up or down, but you can actually pop all of them down or some of them down. And so basically you can make many different configurations out of this surface. So this is what I would call a multistable surface. So there's many different shapes that this surface can take on. It can even take on a like cylindrical shape. If you pop all the units outwards, it takes on a stable cylindrical shape. So this is everything I have for the shape-shifting surfaces or shape-shifting networks. I'm now going to talk about systems that can adjust their stiffness. Again, these are properties that normal structures like beams and columns cannot have, right? So this is, we're really exploring here geometry and mechanics. And I'm going to talk about pressurized membranes first. And I come back to one of my initial slides where I said, well, the way that we are now dealing with storm surge is by building big concrete, stone barriers or nothing. And so my idea is to use a pressurized barrier. So a pressurized barrier is a barrier that consists of a thin membrane. It's actually not so thin, it's 1 to 2 inches. That is pressurized, so inside is either compressed air or water, and/or water. And the wonderful thing is that this could be stored below the boardwalk and could be pulled out when the storm surge warning is coming. Now, this technology already exists at a much smaller scale, so this has been used for dams. What is new here is the scale that we are looking at, so for the barrier, as well as the scale of, or the intensity of the loading, because we're looking here at storm surge loading, and I will talk about that a little bit in a second. So actually this rendering here is actually the same place where, if you remember that slide that I showed you in the beginning with all these people, as the same place, right? So this is Rockaway Peninsula, and we were looking at whether we could, where we could put these barriers. So all our, for example, here, or we also looked at some barriers more inward. And so all of the analysis that we did was with data based on storm surge data from Sandy for this region. So, so modeling this is actually quite complicated because, well, first of all, you have to model the pressure, then the membrane, and the membrane stretches a lot. But then there's also interaction between the membrane and the water, and we're not just talking hydrostatic water. It's not just water that stands there; it's water that pounds on this. So you have to take into account hydrodynamic loading as well as wave break loading. So we built a lot of numerical simulations to study that, and what we found out is yes, such barriers can actually withstand such a kind of loading. And what you see here on the left-hand side are actually 4 equilibrium shapes. So the first shape you recognize is when you have the barrier just inflated, right? It just takes on a semicircular shape. Then when there's water pushing on one side, it will deform slightly. When you have more water pushing on one side, you get actually membrane inversion on the left-hand side. So that is going into not really compression, because membranes can't really take compression, but there's something happening there. And then on the right-hand side, we see what happens if you have water on both sides. So all these shapes are actually defined in literature, and so we found that our models were actually in correspondence with what we were finding in literature. But what I'm not showing here is that we also had to develop wrinkling models and do a lot of studies on whether we should model these as shell or as membrane elements. But anyway, we managed to show that yes, at this scale, for Jamaica Bay and for Rockaway Peninsula, such a barriers would be very feasible. And actually, what makes it so special, actually I forgot to say this, is that as these barriers are pressurized by the internal air, but also by the loading that's coming on from the storm surge, they become stiffer, they become more and more tensioned, and they become stiffer and stiffer and stiffer. It's like when you're blowing up a balloon, if you blow it up more and more and more, it becomes stiffer and stiffer and stiffer. And so that makes that it doesn't actually, as it gets more loaded, it deforms less, which is actually the opposite from what other structures do. As it gets more loaded, they will deform more. These ones, as they get more loaded, they deform less. And so you can actually control the stiffness of these systems by adjusting, for example, the internal pressure. So we check that they don't break, no tearing happening, no resonance, and also there is no overtopping from the water, because this thing is becoming stiffer and stiffer. Another project that I worked on, and this is actually the analogy of the, first I showed you the flexible shells and then the laces, and now I have shown you a continuous surface, the pneumatic shells. Now I'm going to talk about nets. In 2000, and I've put here Cape Cod also, as you might see, because the project I'm going to talk about is a real project, not a real project in Cape Cod, but a real project in Boucron-Canot in Réunion. So in 2005, I received a phone call from Professor Khalid Hadi. He's a professor at the University of Réunion, which is part of France. And he knew that I was working on tensile structures, and he asked me whether I could help him understand the following problems. So Réunion, as you might know, is like next to Madagascar and next to Mauritius. It's a beautiful island. It lives from tourism and it lives from surf. It has some of the best surf in the world until, of course, the sharks come. And you don't need to have a lot of shark attacks, and then the tourists don't come anymore, right? It's not like having a car accident. You can have many car accidents, people still come, but if you have a shark, people don't come anymore. And so, the local government had decided to install a net on 2 beaches to keep the sharks out. And this is what you see there on the right-hand side is the structure of the net. So you have anchored chains, they're anchored to the bottom of the ocean floor. Then you have steel cables, then you have buoys, then you have polypropylene net, which is 40 centimeters, which is about this much. That allows the turtles to go through, but not the sharks. And then it had upper buoys. And this net you see here, it's that green line, that's where it was installed. It was super expensive, not so much because those materials are very expensive. I mean, you could do this with Home Depot materials almost. It's super expensive because it's very expensive to install. You need scuba divers to go onto the ocean floor and then install this net. You also needed scuba divers to go and check the nets every day. And actually, after a couple of months, they were already broken, these nets. So, well, first of all, the sharks. But it was not the sharks. And so he asked me whether I could work with him on trying to understand. Yeah, so here you get an idea of what it is like to be near those nets. You see also some of the damage. This is on a normal day, but so this is in Réunion. So they have, this is in the wave break zone. Remember, this is surfing, so this is the wave break zone. So we get very large forces from the wave break. On top of that, they have the cyclones. So that means that, during certain periods of the year, the water level rises enormously. And so we built, again, fluid structure interaction models of the net that they had installed. We studied these nets under 7 different wave break directions. I already had a hunch, kind of a feeling that the nets that they had installed, that there was something wrong there with the topology. It seems to me, like I thought that was not really going to work very well. And indeed, if you look on my graph there on the left-hand side, you see, number of elements. You see we studied 6 different nets topologies. Of one, the orthogonal is the one in the blue. And as you see, that's also the one that's totally sticking out. So really, they built the worst net, right? And why is that? It's because what I call this net has a very low Poisson's ratio. This net cannot stretch, right? So when the water with the buoys tries to pull it, it can't really go anywhere, and you get large tension in those members. And of course, this is, as you can see, this is accumulative, right? So it's going on, off, on, off, on, off. There is sand between the polypropylene. So these nets really broke as a fatigue problem. And for example, we showed on the right-hand side, you see an hexagonal net, that has much more the potential to stretch out, right? So very interesting. Here we're not working with a continuous surface, but we are working with topology, and some topologies just work much better than others. As I had been working on these nets, I got contacted by the choreographer Rebekah Lazier. She's at Princeton University, who was working with Janet Echemann, who's the artist who works with nets, to see whether I wanted to work with them on a project that involved nets and dance. And so I started explaining to them that these nets have can adapt their stiffness as a function of loading. And so they really liked that idea, especially Rebekah. She liked the idea of the net as a dancer, that depending on how you interact with the net, it will be stiffer or it will be more flexible. And so this is a project that we continue to work on. Okay, I'm going to now talk about rigid shells. Coming from Princeton, we have a bit of a tradition about shells, and how we can design them so that they can actually carry extreme loading. Now, there's lots of evidence, if you look on the internet or wherever you get your information from shells that have withstood very high loading. So we see here some examples of shells, and they're all in red, withstanding earthquakes, tornadoes, or hurricanes. And so we know this. But we wanted to find out why that is. And so we took this shell as an example. This is the Church of Our Miraculous Medal by Felix Candela in Mexico City. And this shell withstood the 1985 earthquake. And so we wanted to find out without much damage. And so we wanted to find out why that is. So we built some models, and we studied the behavior of this shell. We used the linear dynamic statistical analysis to determine the contribution from each natural frequency and see how how the shell will respond to an earthquake. What we found out, and this was really surprising because I got a lot of, "Are you sure this is right?" The eigenfrequency of shells is very high. So the frequency at which they naturally want to vibrate. For this particular shell, actually, it's 3.09 hertz. You see that there on the on the right side. And the peak of the Mexico earthquake was at 0.5, much lower. So basically, these frequencies are not close to each other at all. If they are close to each other, you get what you call resonance, and then you get a lot of structural damage. So these shells have very high eigenfrequency, and what you see here on the left-hand side is the formula for eigenfrequency, right? So it's square root of k, which is the stiffness, divided by the mass. Well, I've already said they're very thin. Okay, so mass, m is very small. K, stiffness, is very high because they are curved. They have what we call not stiffness because of their mass, they have stiffness because of their geometry. We call it geometric stiffness, right? So if k is very high, m very small, our natural frequency is going to be very high, and that is why when we have earthquakes like the ones experienced in Mexico City, these two don't coincide, and we don't get resonance, and we don't get that much damage. So we were interested in seeing what else can we do, we looked at how we could find shapes for arches using graphic statics, and this is of course all very well known to you. Basically it's a technique where you draw the forces and you draw the equivalent shape, and basically the shape which you see here is this blue line is the thrust line, and that needs to fall within the thickness of the arch. And we also incorporated in that the earthquake loading as a horizontal load. And that basically ended us up with a shape like this, like the one that you see in green, but of course the earthquake can come from both directions, so we mirror imaged it, we slightly offset it, we took an envelope, and then according to our theory, this shape should be a really good shape to carry self-weight and also to carry earthquake loading. And we actually checked it with a limit state analysis using virtual work. And so this one was kind of designed to take a 0.3 g horizontal load. And indeed, we found using our virtual work that at that stage, the arch develops 4 hinges and actually collapses. Now, arches, but it's also interesting to see, can we use this for shells? So the idea here is we take one of those lines and the other one, and we offset it with half a period. And then we loft a surface through it, and we end up with a shell surface. So we end up now with a corrugated shell surface. It's important here to note that the 2 corrugations at the base are parallel. Now you might say, well, I've never seen anything like this before. I think you might have, because Eladio Dieste built corrugated shells. Now his shells, these geometries are slightly different, because in his shells, the corrugations, as I said, with us, the corrugation edges run parallel. With him, they are mirror image. So it's not quite the same shape. But actually, Eladio Dieste's model is, and we call it the Dieste model, is a good base model to check our shells against. And so for this, we used a nonlinear pushover analysis to quantify how much loading these shells could take. And actually, we studied 5 different parametric variations that came out of our proposed method and compared them with the STs. How do they vary? Well, some of them have a deeper corrugation depth, and some of them have a smaller period. But what you see in all 6 examples shown here is the way that they fail is that there are 4 hinges formed. 2 at the base, E and A, and then sometimes somewhere one a little bit higher up on both sides, so for example B and D, or sometimes one at the crown. And it seemed that the shapes that developed 4 hinges with one at the crown were the ones that had the smallest corrugation depth, and the ones with a deeper corrugation depth actually developed the 4 hinges more towards the base. And this can be explained because the places where these hinges started to form were the places where we only have single curvature. In the entire geometry, we have double curvature, but the places where you get single curvature is where those they're less stiff, and that's where you get those hinges forming. And so we checked, when do these shells start failing? On the left-hand side, you have a Dieste shell. We see that when we analyze that shell using the pushover analysis, that it fails at about 0.3 G. All the other shells, so you have when the first crack occurs and when the last one occurs, right? So the shell doesn't fail at the first crack. You need 4 locations, so you get 4 hinges, then it collapses, right? So, but you see that all the other ones actually are much higher, and actually the one FF5, right, that is the one that is performing the best, and that is the one that has the deep corrugation depth but very small period. So it's kind of interesting to see that you can actually, and they all have the same amount of material, I have to say that, right? But that you can actually tune the behavior of your shells by introducing these corrugations. Now, one of the reasons that shells have not been built that much recently, people say it's because they're so expensive to build. Because basically what you do is you first build the scaffolding, then you build the formwork, then you all out of wood, then you cast the concrete, and then you take the formwork away and you probably dump it in the landfill. And so basically you're building 2 shells, one wooden one and one concrete one. And so we were interested in, could we build these kind of structures or other curved structures without any formwork or without any scaffolding. And I told you we're going to go back to this dome here, right, the Santa Maria del Fiore in Firenze, which was finished in 1436. It has come down to us through documents that maybe this shell was built without formwork. We don't really know how. We do have drawings. These are drawings from the da San Gallo masons in Italy. They were like generations of masons, right? And these are drawings. And what you see on the left is actually a plan view. What we see courses of bricks, but we see also spirals going up. On the right-hand side, we see actually a section through a double-layered shell. We can assume that if you've built the inner shell, then you can use the inner shell as scaffolding for the outer shell, right? So we're really interested in the inner shell, and on the total right-hand side, you see a rendering of such an inner shell. Again, we see in this rendering, you see double spirals going up. In the picture on the left, you see one spiral going up. So first, people were thinking that these spirals were like decorative things, but actually a lot of these Renaissance domes are on the inside have frescoes, so you can't actually see these spirals. So that made us think that maybe they might have been crucial in how you could construct without scaffolding. So we started investigating this, and we made some assumptions. The first one is that we assumed that these domes were constructed layer per layer of bricks, not in sections or anything like this, right? So not until the first layer of bricks was completed, then they put the second layer. We assume that. And then we also assumed that they had radial geometry, so that when you were constructing this dome, first it's quite vertical, that's all going well, but then at some point, at the angle of equilibrium, these bricks are going to start sliding inwards. And then some magic has to happen because they shouldn't really slide inwards. And that is when we think that these vertical herringbone bricks are gonna stand in, or start going to play something important. So you see the herringbone bricks are in dark gray. The other thing that you also see is that they're actually embedded or fixed in the layer below. So really what happened, and we did many analysis on this actually with all the bricks using discrete element modeling. Basically what starts happening is that once that the bricks start sliding inward, they actually jam against the vertical bricks. And the vertical bricks are stuck in the layer below, so they will jam in there. They will start doing what they call plate bonds. So basically, that's a very flat arch, but unlike the arches we've seen before, you cannot do 4 hinges because this is a too flat geometry. So these arches will push against the herringbone bricks, and then that force is translated into the layer below, and it closes all the courses, and to the layer below, etc., etc., etc. So really quite amazing. So on the right-hand side here, you see a picture. On the top is if you assume that there is no friction between the bricks. So basically, it would be Teflon coated, which is not really possible, because in reality, masonry has a friction factor of 15 or upward. So from a friction factor of 10 between the bricks onwards up, this phenomenon of this plate bond action starts happening. So that's all very interesting, but then the question really is like, how can we learn this? What was interesting here is that we're really using a kind of self-locking assembly as well as gravity to enable a construction that doesn't need any formwork. But how can we construct? Can that be useful to us today, right? Because I'm trying to construct without any construction waste. How can that be useful? So we had the pleasure of working with SOM and the Create Lab at Princeton University, that's a robotics lab, to see whether we could build a shell without any formwork. So I'm going to show you this video. I hope it's going to work. Where basically we are constructing a shell in collaboration, 2 robots collaborating. One is adding a brick, the other one is supporting the structure, and the humans are controlling this. not again. All right. Okay, so that actually brings me to the end of my talk. I hope that I've been able to show you that we can actually use the extraordinary mechanics that are embedded in geometries or that are embedded in topologies to make our structures do things that other structures can't really do. And this, we're going to really need that because, we are facing all these huge challenges that we need more floor space, that we have, much bigger loadings, and that we don't want to create any waste when we are building that. So in brief, I hope that I've been able to show that, we studied interaction between these slender surfaces and the environment, or how they behave under construction. We draw our inspiration from biology, craft, or history to inspire new structural systems that maybe haven't really been studied before. And in order to do that, and I haven't really talked about that much here, but we developed numerical, machine learning, graphical, and also fluid structure interaction models to generate knowledge in this domain. Thank you very much, and I'm happy to answer any questions you have. And of course, I need to thank, because these are the people who do really all the work. These are my postdocs and my PhD students, and they really do all the work. So thank you to them, thank you to my collaborators, and thank you to my funding bodies. Yeah.
All right, thank you, Sigrid, for such an inspiring and impressive body of work and so beautifully presented.
Thank you.
So the plan now is that Sigrid and I will have a quick conversation for 10 minutes or so, and then we're also open to your questions, either online or from our physical audience. So please write your questions down on an index card, and they'll be collected by our staff, and they'll be brought up here as well. So we're looking forward to your questions as well. Mm-hmm. So first of all, Sigrid, thank you so much again for sharing this work. Really exciting for all of us to see. The first question that comes to mind for me is about collaboration, because it's very clear that your work is incredibly collaborative and broad in aspirations and applications. So can you share any wisdom or your philosophy on how you see collaboration? And it seems like you collaborate both with artists and architects, but also with scientists. How does that work best for you?
It's a good question. First of all, I am quite a social person, so I like working with other people, and then I like working with people that I like. So, so if I get to work with like funny people, I'm all up for that. But I think I see myself maybe not so much as like just an engineer or like. Also, you mentioned, for example, the university that I went to, the University of Bath. It was a bit an unusual school or university because they taught architects and engineers together. So in the first year, we had all courses together. And it was quite interesting because we didn't know from each other who was an engineer and who was an architect. Like at that stage, you are not so kind of disciplined, informed, like, oh, I should only talk about this because I'm an engineer, or I should only talk about this because I'm an architect. And actually it was quite funny because after 1 year, when we really had to declare we're going to do this or I'm going to do this, it was quite surprising. Like from some people, I thought they were more artistic, but actually they became engineers. And then in the second year of that course, we had mandatory sketching. We had mandatory sculpting courses. This is in engineering, right? It was a very small engineering school. I loved all that stuff, so actually I took many more sculpting and engineering courses outside of the curriculum because I thought, oh, engineering is so cool, we get to sculpt and stuff like that. It was only later when I went to other, I've taught at a few places. When I was teaching in other places, I realized, oh, this is not really how other engineers are taught. They don't know how to sculpt or paint or sketch. And so I think, although I am in the Department of Civil and Environmental Engineering, and I'm really a structural engineer, and sometimes I'm a structural designer, I think I don't really see myself as being in one of those niches. And I think that is because of the way that I was taught. Also, all the people that taught there at that time, Ted Happel was teaching at the time, Chris Williams, these were people that had very broad interests. I had, for example, history of engineering from Ted Happel. We would learn about a lot of stuff. We went on site visits to Italy, for engineers, what do engineers go and do in Italy? And this was all very normal. We had to spend one day sitting on a square, drawing the entire square over and over again. And I thought that was engineering, I thought that's engineering education, right? And so I think that makes that I don't perceive myself like, I can only talk in this way. And also afterwards, the people that I have met, for example, at Princeton, I'm co-teaching a course with a sculptor. And it's amazing how similar we think. Because also, if you make a sculpture and you make a joint, the joint should not fail, right? Like whether you're a sculptor or an engineer, in both cases, they should not fail. And so I find also now working, for example, with Rebekah, the choreographer, like the things that she talks about, this net becomes stiff, and if we do if we go and stand here, we can feel these lines, these very rigid lines. Yeah, so this is where the stresses are the most. So she's maybe using different words, but of course, the experiences, the physical experiences are the same. And this is something that I try to advocate for in teaching, is that we don't only teach through calculations in engineering, but that we also have a lot of haptic experiences, so that we learn by doing stuff with our hands, by feeling things. There's a lot of resistance in this, that means that there's a lot of strain energy in this. So I find that in other disciplines, of course, there are also people, so they feel this, or they experience the same things. They might use different words, but if you have a conversation and you can say, when they're talking about this word, what they really mean in engineering sense is second moment of area, right? So I don't know. I don't really find it very difficult to work with people from different disciplines because, there's common sense. Gravity is gravity. We feel things in the same way. So I don't know. I don't know if that answers your question.
Yeah, no, beautiful. I agree that sort of universality of our own experiences as humans in the world is a great way to find common ground with other disciplines. Pulling on one of the things you just said about kind of equations and calculations versus more haptic and physical intuition-based understanding, how do you see you talked a lot about, history and kind of physical intuition in your talk, but you also obviously use a lot of sophisticated software tools and advanced technology. What's the relationship between those kinds of ways of thinking for you in your work?
Yeah, so I think intuition is very, very important. Before you start building a complicated whatever model, you kind of have to know what you're going to expect. Although, of course, there can always be surprise. And I'm not saying that out of these numerical or digital processes, you cannot get very unexpected results, which are always surprising. But I think we have to always understand from our kind of intuitive and physical understanding how these things work. And so, for example, I teach a class on form finding of structural surfaces. This is a graduate class taken by engineers and architects. And in that class, we both do physical form finding. So we make models with hanging plaster models for shells and lycra models. And then once we've done that, we learn the numerical techniques for that. But I think it's very important to have an intuitive understanding of how forces go. If you bend something, how much resistance there is of that thing in your arms. I will tell you, it was very funny, even for me, right? Like I've been doing this now for a long time. In the performance with Rebekah and Janet, so we had these nets, right? And of course, nets are tension structures, so you need to kind of tighten them down if you're going to dance in them. But of course, we were doing this performance in a beautiful hall, so we can't really tighten them down in a beautiful wooden floor. So we didn't find anything better than having big wooden tree trunks and attach the nets to that through pulleys. And during the performance, so the dancers are in the nets, And I knew that one of the tree trunks was not so big, so I thought, well, no problem, I'll go and sit on it, right? Then at least it will for sure stay down. And at some point, I'm sitting on this tree trunk and it lifts up. I'm like, oh my God, that's uplift force for you, right? Like, and I knew this was gonna happen because it had happened, but just to feel this enormous force was for me, even like 2 years ago, quite a revelation, as in, wow, these nets actually take a lot of force, and when you anchor them down, whether it's for dancers or you're anchoring them down for wind uplift forces, you know, those forces are huge. You know, they can lift me up. Yeah, anyway.
Excellent. Yeah, that sounds like an amazing experience.
Yeah.
I'm gonna switch to some questions from the audience here. So this question asks for you to speak a little bit more about the trade-off between material efficiency and, you know, thinking about embodied energy and carbon versus kind of resilience and robustness in extreme events and dealing with extreme loading. You talked a little bit about that, but can you speak a little more about that?
Yeah. So I think there was at some point a kind of, how to say it, trend or thinking that, you know, we should like do optimization and remove all the material that is necessary. But of course, we have learned through history and things that have happened that we need resilience in systems. We need different load paths so that if a column fails, that, you know, not the entire building falls down, and there's actually different load paths. The good thing is with all these systems that I've shown, whether they are surfaces or networks, if some members go, or if there is a hole made in the membrane, then the forces will find their way around it. And that is really the wonderful thing of these structural surfaces, that that there is actually redundancy in the system, that the forces will always find another way to channel themselves down to the foundations. So we've learned this, right, that we need resiliency and redundancy in systems, because we cannot rely on components to be totally essential. And especially, for example, in tension structures, right? If you design tension structures, you cannot just design them to their bare minimum, because if somebody comes along and cuts one cable and the whole thing falls down because if your one cable is snapped or somebody has vandalized it, we cannot have systems like that. So it's a trade-off, but I think it's essential. We cannot live with systems that just have the bare minimum on them.
This next question asks about kind of the past and future of the built environment. How do you see our built environment transforming due to the techniques you're proposing? And interesting, what happens to what's already built? Where does it go? Is there a way to restore and work with what we have and not just build and continue to build? Provocative.
Yeah, so I think we're going to have to build in a totally different way, and I see some really good things happening. I'm very hopeful. For example, I'm very hopeful for the use of wood, timber. I'm very excited about the renewed interest in that. And I think, what the work that you're doing, Caitlin, with embodied carbon, I think that's so fantastic that this is now becoming so important, and that you're teaching students that, this is the way that you're going to have to design. But indeed, we are stuck with, with a large building stock. It's not all beautiful domes like the ones I've shown you, because of course there's one thing is cultural heritage. We need to preserve that to remind us of who we are and who we were. That's important. But there's also a lot of building stock out there that is maybe not a really cultural heritage. And actually, I've been very pleasant surprised. I arrived a little bit early, and I was walking around here in the neighborhood. I'm very thrilled by seeing how all the old brick warehouses, I was like, what's this? Well, a brick, well, I don't know if they're warehouses, but like brick buildings, and then on top of that, the huge buildings. And I don't know maybe if this is a controversial thing, but I had not seen that before. And I think that's kind of interesting. We're going to have to find ways to, I see you smiling, so I don't know what, you probably have
our school, the School of Architecture and Planning is hopefully going to move to one of these brick warehouses.
Oh, I see. Okay. But we're going to have to find new ways to renovate them, and of course also make them suitable for today's and future's needs, right?
Another personal question. What would you say to young people in general, but also with diverse interests spanning engineering, architecture, and design? How did you choose your major and your career path?
Ooh. Yeah, I was thinking about that. I didn't actually know what I wanted to study, so I signed up. I was going to do a major in French or Arabic studies or public policy. And then I actually didn't really know what I wanted to study. And so I went, which now is not so weird, but like a long time ago, it was weird. I went to England for a couple of months and I just did stuff and I like that. And I think what has been a kind of common thread through the decisions or the things that I have decided to do, I've just followed, I've just done the things that I thought were interesting rather than the things that people thought that I should be doing or the things that people thought that would lead me to a good job. So for example, I'm originally from Belgium, but I studied in the 90s or 80s, I think now. In the 90s, I studied in the UK. There was nobody doing that. Like I've met 2 people in my life who've done that because we have really good universities. In Belgium, you wouldn't really go to the UK. People were telling my mom, oh, she'll never find a job, if she comes back. And I was more thinking it'll be an interesting experience. And then I stayed there for 9 years. And then, then maybe I shouldn't really say what I did afterwards, but actually I went to live in Mauritius for 2 years next to Réunion. That was really great. So I've always, I think, done stuff that is a bit unconventional. I think the other thing also, you should learn things that don't really lead to anything. I find, a lot of people, John applauding, because I see a lot of people take these courses or learn this because that's going to make me jump through the next hoop. I think you should just learn things that are maybe totally useless, but become really good at them and enjoy them because those might be the things that actually take you the furthest in life because you will be the only one who knows how to do bobbinlacing. That's a dying craft, right? Not totally dying because there's a whole contemporary thing, but like nobody does that anymore. But you should learn things, I think, that you just find fascinating and don't really pay too much attention, I think, to what people say, oh yeah, you should be doing this. So for example, when I was 18, everybody in my class was doing business administration. That's what I would have done normally if I had done what everybody did and what my parents suggested I would do because I didn't really have any ideas I had too many ideas of what I wanted to do, but none of them were like very suitable, I think. So anyway, I think you should, just follow what you think you should be doing. And sometimes I think it's quite difficult today because there's so much pressure, especially in courses. You must get good grades. You must, in order to do the next step, etc. But I think you should never really forget who you are and what your passions are and what you love doing. So, for example, it's funny. I loved making baskets. When I met my husband, I said, "Oh, if there's any time a big war, don't worry, I know how to make baskets." He was like, yeah, great skill. But actually now with the torsion thing, like, okay, we're doing networks that kind of pop out and I'm like, oh yeah, we can make this out of wood and we just have to make it wet and it'll be more flexible because I remember we used to be, anyway, so like I have some advantages if you do totally useless stuff.
Yeah, that's really great advice, I think. I often talk to students who feel paralyzed because they're interested in so many different things, and they also are so concerned with the huge challenges that we all face, and they want to do something about them, and sometimes they don't know how to get started. And it sounds like your advice is to just kind of follow what you personally are most attracted to. But do you have any more beyond that to add?
Yeah, and I think also like for places and people, right? You have to feel what feels right. Like people might suggest, oh, you should do this, or you should, I don't know, you just have to try to not lose sense of what is important to you as a person, irrespective of what everybody else is thinking you should be doing, where you should be, who you should hang out with. Just, I don't know, try to, I don't know how to say, like, try to feel who you are, and then it'll come out.
We have a few more minutes. Do you mind if I return to extraordinary mechanics for the last few questions? Is that okay? There's a lot of questions about inflatables here.
Oh, okay.
I think inspired. Maybe I'll pair them and you can answer them however you like. One of the questions asks about how you imagine the inflatable storm barriers will be deployed rapidly in response to an extreme event. And then the second question I think is interesting is asking about the potential for inflatable formwork for shell structures.
Yeah.
Which I believe I talked to you about 10 years ago when I went to your exhibit at the Princeton Library. Anyway, please, I'd love to hear your thoughts.
Yeah. So, remind me again, how can they deploy? So actually, they can be deployed quite quickly. So you do this with air compressors, just like you would. Of course, this will take some organization. So some of these huge inflatables have been used, for example, in the Netherlands, not for storm surge loading, but for other kinds of loading. And there it gets deployed quite quickly. And there actually they said, if this system is going to fail, because also another question I sometimes get, what happens if it gets punctured and the whole thing goes down? That's not good. So for failure, right, in the membrane itself, there are ceramic chips for debris to stop it, but also it's compartmentalized, right? So it's not that you are inflating the entire sausage along Rockaway Peninsula. It's compartmentalized, so you can actually inflate many different compartments at the same time. Another thing you can do is actually have not only one membrane. It's a little bit like when you design glass structures. You don't just have one glass, because if that breaks, you have glass and then some kind of a sticker in between and another glass, so that if the one glass breaks, it doesn't fall down, and secondly, the other one takes on the structural action, right? So you have redundancy in that system. So you would have that also in the pneumatics. And then the other question was about
inflatable formwork.
Yeah. This is very interesting, and as you probably know, this has been done, right? Like there is in Australia, this has been done. The Bleeny shells, right, where they put the inflatable on the ground, they put the concrete and the reinforcement, and then they reinforce it. In the United States, I believe, in the Midwest, domes are being built like that. And there has also been some interesting work recently in Austria where they don't actually pour the wet concrete and then inflate it, but actually have precast elements and use the big inflatable to lift it all up. And then, this is all in segments, and then they kind of join the segments together, and then they deflate the shell. So, that's a good idea. People are working on this idea, and you can do it either with the fresh concrete. The challenge is with the fresh concrete is when you inflate the shell, you have to inflate it hard enough, because the concrete weighs, and what you don't want is to get that inversion that I talked about of your membrane, right? Because if your membrane is done like this, then you get a shell looking, it'll dry, and that's not a good idea. Another way that I'll stop talking about formwork. Yeah. Please, I can just keep on going. No, it's enough.
Are you sure?
Yeah, it's enough.
I might move on to a more challenging question from one of our audience members. So this person is asking about the famous McKinsey chart that you showed in the beginning that
not looking very good. Yeah.
Indicts all of us for our lack of productivity, but. So this person asks, do you think that automation is the only way to improve the construction industry, or do you think there are other ways that we can address this productivity gap?
Yeah, so I think one is indeed construction practices. I haven't really talked about this much. So one way would be to use robots in different ways, and we're currently using them in the construction industry, because we are using robots, but that's always for very repetitive tasks and just heavy tasks. But actually, robots, as you probably know better than me, can be used for very customized work, very differentiated work. They can support stuff. And so I think if we go down the road of robotics, if we can also embed the robotics with some kind of artificial intelligence, we could actually start building not predetermined designs, like, we're going to build this vaulted structure, but actually embedded with rules, as in it has to span this much, these are the structural rules, we need 2 openings here, and have the robot actually decide what geometry this is going to be, or maybe with some input from the user. But that is robotics, but that is just one avenue. I think actually we are already in a very exciting moment where we are exploring some of the things, and MIT is a really good place to be at, because I think one is taking embodied carbon as a design philosophy, and maybe that's not really the word, but really taking that at the core of everything you do is a way forward of designing and building more efficiently. Okay, so that's another path. Another path is, of course, also, and for you this is all very obvious, but you know, when I was an engineering student, my professor said, okay, all your truss lengths have to be the same length, right? And all your bolts have to be the same. That's not so long ago, and there are a lot of designers that are not really designing, thinking, taking into account the entire potential of digital and digital and robotic, or what's the word? Digital and digital is the designing, but like the manufacturing, right? Digital manufacturing. It's a very exciting, and I think that we have really not yet completely seen where we can use these techniques for to really drive us, so that we're going to have new construction methods, new structural forms that weren't really possible before, because before everything had to be the same length and the same node and the same bolt. So we are actually at a very exciting time, I think, for architects, for structural designers, because we have many challenges. So if we find good approaches, these are going to be taken up very quickly because a lot of floor space is needed. And there are a lot of exciting things already on the books, and you are here, I know, learning about all these things. You're learning how to use these techniques. So that's all very positive, but robotics is not the only way. There's many other ways that we're going to be able to do this as well.
All right, thank you so much, Sigrid. So we're just about wrapping up the evening, so I just want to thank you again for such a inspiring and thought-provoking talk and discussion. I think, you know, extraordinary mechanics and even ordinary mechanics are really wonderful
Ordinary's also pretty good.
ways to improve our design processes, and I hope all of the students and people watching at home are inspired to push themselves further to figure out how to use them in their own work. So with that, please join me in thanking Sigrid again. Thank you. And
you have to deal with me again, but just briefly. I said you have to deal with me again, but just briefly. I would like to thank you all for coming tonight, and thank Sigrid especially for an amazing and really inspiring lecture in the best tradition of all we're trying to do with the Allen Lecture. And finally invite both you here in the audience and our audience online to join us for our next Fall 2021 event on October 14th in the Long Lounge for those of us here in person, in the very same place on the web for those online. And at that, on that evening, we will again welcome into our lecture series the Conversation on Care series led by Professor Anna Maljachki, and she will be introducing to our community Mfo Matsipa, based in Johannesburg, this year Loeb Fellow at Harvard, and Director of Studio X in Johannesburg. So please join us on October 14th, and thank you all for joining us tonight.